to trickle in here. So let's see, did I turn that on? It's so hard to tell in this system. No, yeah, it's on. Okay, all right, good. Madison, I wanted to ask you first. Did you pick a Wednesday time or a second time, or is it just going to be once a week for your SI session?
Oh, my essay sessions are going to be, I'm going to have 2 per week.
Uh-huh.
So my first one is from 12 to 1 on Monday.
Right.
And then my second one is from 9 to 10 on Thursday. So,
Thursday. Oh, okay. All right.
Mhm.
So, all right. So 9 to 10 on Thursday. So just a little bit before this class. So that's convenient for those people who don't have class immediately. That's convenient for people who don't have class immediately before this one. So Madison sessions will be, and I'm sure all of your ID information is posted there in Blackboard, your Zoom ID information. But so Madison sessions will be 12 to 1 Monday and then 9 to 10 on Thursday. Okay. So the Thursday one might be especially convenient because I haven't adjusted. We have another homework that's due. I don't know if y'all can see this. If it's, let me wait. Let me.
Oh, we can see it. Yeah, we can see the due date.
Well, let me go. Let me go to the student view. So.
Oh, okay.
All right. So there's student view. So the homework that was due on today, I slightly adjusted that. Most people have made good progress on that, but I just added an extra day. So it's due tomorrow at midnight. So this one is very short, and I'm going to look at just one problem on this one, but you can ask other problems on this homework, this first homework that's due. And then I have another one still scheduled for Thursday. So we'll check and see where we are on Thursday. These are both short, though, not that many questions. So, and I think they're really just review questions. So you should be, pretty good at doing these problems. Even before the class started, you could have done these problems. So, so for the time being, I'll leave this one at Thursday, but then you can ask questions of Madison maybe on Thursday morning if you get a chance, if you're, if you have certain questions about this. So I'm going to look at this, just a problem off of this homework, but if you have other questions that you want to ask about this one, you can. So I'm going to open this one, and then, but also feel free to jump in with questions if you need to. Let me see if I can move things around so I can get to my scroll bar here. Okay, so the only question I want to look at, which is really not a hard question, but I just wanted to make you aware of something, is this question number 2, which is just graphing a graph. Okay, so it's just making a graph. So it suggests that you make the graph by plotting points. So that means, you want to find points that are on the graph, right, and plot those points, and then, try to connect those points, with a curve, right? So just the very elementary, naive process for making a graph of this, relation, making a graph of this equation. But most of the time in this class, we're not going to make graphs by point plotting, because that's just too elementary for us. We're trying to use more sophisticated techniques here for making graphs, and so calculus is going to help us a lot with making graphs. But of course, at this point, we haven't really learned any calculus. So the way I would suggest making this graph is by using a computer or a calculator, okay, rather than trying to point the plots by hand. When you use a computer or a calculator, by the way, that's what the computer or calculator is doing. It is doing a sophisticated version of point plotting. Of course, the reason it does it so well is that it can plot lots of points and connect them very quickly, right? So so when you use a calculator or a computer to make a graph, you are essentially doing plot pointing and point plotting. So I wanted to show you, this is the tool that I'm using in class, right? And so you've seen it a couple of times already, me just using it. And I just want to remind you that you are free to use this, but you can use a graphing calculator as well to plot your graphs. So this is Desmos, and you can find it at www.desmos.com. So it's easy to get to on the web, and then just choose I think it's Start Graphing is the button, and that you would choose, and it's going to show you a screen like this, which is just a blank, rectangular coordinate system, right? And then you would just type in your, you're just going to type in your formula, over here on the left-hand side, pretty much as you would see it written. Pretty much as you would see it written, on the page. So let's see if I can find. Did I close that? No, here it is. Okay, so there's the formula that we want to plot, right? Y equal 1 over x plus 2. So, you can just come here and just start keying that in, right? So just y, and then, find your equal key there, if I can find it. And there it is. And then, whoops, let's not use capital Y, but we could use capital Y. So y, and then equals, and then a 1, right? And then the slash there will give you division, if I can find a slash key on there. So there it is. I already typed that wrong, of course. So let's go back. 1 divided by, and then x plus 2, right? And as you start filling in the expression, by the way, notice Desmos is always graphing. So when you have a valid expression, Desmo will already graph it for you. So there's the plot, and so see, that's and now it's easy to answer that question, right? Okay, so you can see Desmos gives you a really a nice plot. Notice that the curve there appears to be broken at x equal -2, right? So notice that the curve does not appear to cross that vertical line x equals -2. And we'll talk more about that today, but you already probably know why that's the case, right? Because if you try plugging -2 into this expression, right, for x, you're going to get 1 divided by 0, which is undefined, right? So so you cannot use -2 as an x coordinate in this expression, right? Okay, and so that means in all of the ordered pairs, which are in this relation, and there are billions and billions of them, right? All of the points on these two branches of the curve, right, are part of this relation. But there is no point in this relation with an x coordinate of -2, right? Okay, because this equation is not valid for x equals -2. So indeed, this curve does not cross over this vertical line x equals -2. Was that one of our choices there on the? Was that one of our choices there on the? Of these 4 choices, do we see it there? Yeah, here it is, right here. So it looks like number A was the number A, or I don't know if that's A, but the first choice there was the choice that was the correct graph. All right. So again, remember, you can just use this software, www.desmos.com, or to easily make graphs, or if you've got a graphing calculator, or if you have some other software you like to use to make graphs that you may be familiar with from your other classes, then feel free to use those. I mean, the Windows 10 calculator also will make graphs for you as well. So if you're using Windows laptop, then with 10 on it, then you can make graphs just with the Windows calculator. Okay, so we are going to be relying on computers and calculators to help us make graphs. This is the one I'm going to show you repeatedly in class though, because I just like the graphs that it makes. I will try to include in the future links in your homework instructions to Desmo, so you won't have to be constantly typing in though it's not hard, so you won't be constantly having to type in the Desmos URL, but I haven't done that yet. I thought I had those links included, but they're not in the homework instructions, so I just have to copy those back in. Okay. All right, so do y'all have any other questions on the homework on this assignment that's due actually now tomorrow? Anything you want to ask about that? So I had a few people now that did not start the second homework, the one that was due on Saturday, and then a few people started it but had really low scores on that. So try to make sure that you're keeping up with your homework. Okay, so you've got to make a special effort to finish your homeworks by the due date. It's possible that you just forgot the due date. Okay, usually I send a reminder email, but I didn't do that on Saturday. But so try to remember when the due dates are for the homework and try to keep up with those, right? Okay. Because the homework is going to be a really important part of the class. So it's not going to, your grade is going to suffer if you're not keeping up. Your grade is going to suffer if you're not keeping up with the homework. I still have a couple of people who are not enrolled officially in the class. So Andres, we already talked with you, right? You're just having trouble getting the key entered, the class ID entered properly. So we'll see if we can figure that out. And there's someone else. So if you're not already enrolled in WebAssign and you're in the sound of my voice, try to get enrolled in WebAssign. I think the free period is ending today. So at some point here, pretty quickly, you're going to have to actually pay and register. And a lot of people have already registered. Most of the class have registered. So try to do that quickly. I know there's expense associated with that, and so it may take you a few days to do that, right? But try to do that as soon as possible, so we're not getting too far behind on the homeworks. Okay. All right. So any questions on the homework or other questions about the class while we have a chance here that you want to ask? Well, I've got questions for you today, so we'll get to those pretty soon here. Let me actually, since I'm mentioning it here, let's try just a little bit of a reminder of where we were at last time. So I've got just a really simple poll question. So let me see if I can find the right poll though. I got a lot of polls here, so let me see if this is the right one. Yeah, I think it is. Okay, so I'm going to launch this one and see if you remember. This is the last thing that we talked about last time. So are y'all all seeing that?
Yeah, we're seeing.
Someone's whispering, but I can't hear very well. All right, somebody's seeing it because I'm starting to get some answers, right? So the question is, what key property makes a relation a function? Remember, function is a special type of relation, and this is really the type of relation we're going to focus on, at least here in the first part of calculus. And so what makes a relation a function? All functions are relations, but not all relations are functions. So what special property makes a relation a function? Yeah, we're getting all sorts of answers here. So keep voting, try to vote there. And there's no penalty for getting the wrong answer. So just what the first thing that comes to mind. This is just kind of recall practice. So that's good for helping us get started on a class. That's why I do this. All right, so I'm going to end the polling here. Most people have voted. Actually, almost everyone's voted. So so let's see what y'all put there. Okay, can y'all see that the results there? So so we got a kind of a wide variety here of answers. So the first one says, here's the most popular answer: each X has exactly one matching Y. Remember, a relation is a set of ordered pairs, right? So every ordered pair is going to have an X, a first coordinate, right? And a Y, a second coordinate. And indeed, this choice is correct. Okay, each X in a function, each X matches exactly one Y. Okay, so you don't have in a function the same X matching different Y values. Okay, each first coordinate matches exactly one Y value. So if you answered that one, this is true. But notice some people answered the second one. Two or three of you answered the second one. And if you read this carefully, it says no two second coordinates match the same first coordinate. Well, if no two second coordinates match the same first coordinate, that means every first coordinate matches only one second coordinate. So actually, the second answer here is the same as the first one. All right, these two statements are equivalent to each other. So this is also correct, right? So if you answered that one, you were still correct. And the third one also is equivalent. For each X, there is one and only one matching Y. That's equivalent to the first two. So technically, the actual right answer here is all of the above. All of these three statements are really saying the same thing. Okay, so if you got one of them, any of them, that's good. Okay, because they all really mean the same thing. So remember, in a function, each X coordinate matches one and only one a Y coordinate, right? Okay, that's what makes a function a function. Okay, so I'm going to switch back to the notes right where we left off last time, and we're just going to continue. There are a review of functions. So I know you're pretty aware of how functions work, but since this is so pivotal in calculus, I have to make sure that we understand it really clearly. All right. So let me switch my screen sharing here and just to the notes. And okay, all right. So there at the top of the notes, there is our that's our definition of function, right? Okay, and we were just playing a little bit with that. We were just playing a little bit with that definition last time. Okay, and so we were looking at some examples of relations that are functions, and we looked at this example number 2 here, where I gave several relations in the form of tables, and we just discussed which of these relations were functions and which weren't. Okay, and I think y'all did really good job with that. Okay, one thing to remember about functions is, remember, functions are relations, so you can graph them, right? Okay, and but when you graph a function, the graph of a function is not going to have any loops in it. All right, and so graphs of functions are less complex than graphs of relations in general, and that's one of the things that makes functions attractive to us to work with, especially when we're first studying calculus, is the graphs of functions. Although they can be complicated sometimes, they're not as complicated as the graphs of relations in general can be, because graphs of functions do not have loops in them. All right. Okay. So now I'm going to introduce here some terminology to you about functions, and probably this terminology is going to be largely familiar to you, so that's good. This is just meant to be a review, but if it's not a review, then that's fine. Okay, it's not hard to learn this terminology for the first time. Okay, so again, functions are relations, right? So relations are set of ordered pairs, right? So in the ordered pair, in a relation, right, you have a first coordinate and a second coordinate, okay? And so oftentimes now in practice, we will use a letter to represent the first coordinate, a variable, in other words, to represent the first coordinate in a relation. Whatever variable we choose to represent the first coordinate in a relation, I'm going to call that the input variable. So typically, 99% of the time, that input variable is going to be X. All right. So that's the letter, that we often use to represent the first coordinate in a relation. That's why we often call the first coordinate the X coordinate, right? Okay. But if we choose other letters to represent the first coordinate in a relation, then our input variable, that's the name for that letter, might be different. Okay. So sometimes another a common second choice, another common choice for an input variable would be T. All right, we often see used as the input variable. Okay, and the letter then that we use to represent the second coordinate in a relation or in a function, in a relation as well, but in a function in particular, that letter, we're going to call that the output variable. So again, most of the time, the output variable is going to be Y, right? You usually think of the second coordinate in an ordered pair as being Y. That's why it's often called the Y coordinate. So that letter that you use for the second coordinate, that's called I'm going to call that the output variable. So if you hear me use the term input, I will use that frequently. You can think of X, all right? If you hear me use the term output, you can think of Y, all right? So sometimes I'll be interchanging the terms that I'm using here for X and Y. Sometimes I'll use output and input rather than X and Y, okay? And often now we use letter names also to represent the function itself, okay? So the letter names that I often use to represent functions are F, G, H. Those are common names that we use for functions, but we can use almost any, we can use any letter that we like to represent a function. These are the ones that you see most frequently, however. But remember, the function name is the name of the function, okay? And a function is a relation, right? So, so when you give a name to a function, you're giving a name to the entire relation, right? Okay, as opposed to the input variable and the output variable. Those are just used to name the individual coordinates in the ordered pairs of a relation. All right. Let's use an example here to illustrate this, and this is going to seem like a very familiar example for a couple of reasons. Because one thing, I'm going to go back and use this same story that we've used here since the beginning of the course. So remember that relation that we've been using, right, to relate the life expectancy, right, of female high school dropouts to a lapsed year after 1990, right? So here was that equation for that relation. Okay, and if you graph that relation, you can only see it partly here on the screen, but if you graph that relation, you notice that you're going to get a straight line, right? Okay, so here's the equation and here's the graph, but same relation. So of course, now we can solve this equation for Y, and we did that before, right? And when we solved the equation for Y, right, which is the second equation, you can immediately notice, right, that, oh, this is a linear relation, right? This is a linear equation, and you can read off what the slope is, right? So the slope is minus 0.22, and you can read off what the y-intercept there, which is 78, correct? So, of course, that's why when we graph the relation, we get this straight line that you can see over here on the right. Okay, all right, now, so there is just a relation in general, right? But notice that for this particular relation, right, for this particular relation, whenever you choose a value for x, in other words, when you choose a value for the input, right, here, okay, you're going to only get one value for y. You're only going to get one value for the output, correct? Okay, because that's just the way the calculations in this equation work, right? If you substitute a number for x and do this arithmetic, you're going to get one and only one matching value for y, correct? So notice that this relation is also a function because each input is matched with, or each x value is matched with one and only one y value. Okay, so so this linear relation is also an example of a function. All right, so it's a simple example of a function, but it's an example of a function. So we can emphasize that fact now by using what is known as function notation. Okay, so function notation is a special notation that we use just for relations that are functions. So we don't really use this notation for relations that are not functions. All right, now let me show you how function notation works. Okay, but I know you're familiar with this, but I just want to re-emphasize or remind you of how function notation works. So again, this only applies to relations that are functions. So you're not going to use function notation for relations that are not functions. So things like circles are perfectly good relations, but we don't use function notation when we're dealing with a circle. All right. Now back to function notation here. Here's the way function notation works. First, you're going to pick a name for the function, right? Okay, so you can pick any name that you like for the function. Again, one that we frequently use that you're familiar with, right, is f. So in this example, in this high school dropout example, I'm going to use f as the name for my, I'm going to use f here. I can get my pen to work. I'm going to use f here as the name for this function. All right. So again, f is the name for the entire function. So f refers to that entire straight line that you saw graphed there, right? Okay. For instance. Now, that's the first part of function notation. So I picked a name for the function, right? Okay. And now I'm going to express the fact that we have a function here by writing this equation. Okay. So I write y equals, and then I'm going to use this expression. Notice you write the name of the function and then parentheses, and then you have the input variable inside the parentheses. Okay. That is called function notation. That looks like multiplication because it looks like you're taking f and multiplying it times x. But remember, f is not a number, all right? F is not a number. F is the name for the function. So this is not multiplication. Sorry for the confusion in mathematics. This is one of the cases where we're using notation that's a little bit ambiguous what it means. That happens sometimes in mathematics. And you just have to understand from the context what this expression is telling you. The way you can distinguish this from multiplication is, remember, f is the name of the function, and we don't multiply functions times variables like this, okay? Now, since this is not multiplication, do not read this off the page as f times x. That is not f times x. You read this as, you can't read that very well, but that's the word of. So you read this off of the page as f of x, f of x. So if you read that equation across, you would say y equals f of x. Now, what does that mean to us? Okay, you know, you can read it off of the page, but you know, in practical terms, what is that telling us? All that telling us is there is some function, right, that relates this quantity y to this quantity x, and the name of that function is f, okay, right? The name of that function is f. And it tells us a little bit more. When you choose a value for x, you're going to get one and only one value for y. Okay, that's really important. When I choose a value for x, I get one and only one value for y. All right. So again, you read this as y equals f of x. Y is a function of x. Okay. One value for x is going to give me one value for y only, right? Now, I also wrote here the formula for this function because we know how this function works, right? If you take your value for x and you multiply it by minus 0.22 and add 78 to it, that's how you get the matching y value, correct? Okay, so I can also fill in this expression on the right just to indicate how this function works, okay? The way you take an x value and get the matching y value is you take the x, multiply it by minus 0.22 and add 78 to it, okay? All right. Now, when I explained that kind of abstractly, it's a little bit hard to grasp kind of the significance of function notation, right? I get that. Okay. So we have to look at an example before any of this makes any sense, okay? But I do have just a couple of margin questions here. These are things to think about, right? Or things to remember about this series of notes. What does y equal f of x mean? Okay, that means y is a function of x. So if you pick an x value, there is some rule. It might be a formula, or it might be a graph, or it might be a table, but there's some rule, some relation you can use, right, to take that x value and find one and only one matching y value, right? Okay, so when you write this equation down, that's what that means in practice, okay? Oh, if I'm given an x value, there's some way I can find one and only one matching y value that goes with that x value, right? Okay, and how do we read this expression off the page? I just read it. Y equals f of x, right? Not y equals f times x. This again is not a multiplication. Okay. All right. Let's try to solidify this with some examples that are going to seem probably easy to you, but and that's great. Okay. I want them to seem easy because function notation is really easy to use, but it's one of the things that students sometimes get hung up on. Because I think it's easier than it seems. So they want to make it more complicated. They want to make it more complicated than it is. Okay. Does someone have a question before we launch any further into this, though? Someone want to ask me something? Okay. All right. So I've got really several related examples here. So here's one where I'm just going to tell you. All right. So again, referring to that same function, as in that life expectancy function that we've been discussing, right? If you write down f of 12, okay, if you write down f of 12, what that means is, right? What is the y value that matches an x value of 12, okay? So when you write down f of 12, that means the y value that matches an x value of 12, okay? An x value of 12, that's 12 elapsed years after 1990, so an x value of 12 means the year 2002, right? Okay, and so f of 12 would refer to what is the life expectancy in the year 2002, right? Okay, and if we use our formula to calculate that, that formula that we have on the previous page, you end up with 75.36, okay? So f of 12 means the life expectancy after 12 elapsed years after 1990, that would be 2002. That life expectancy is 75.36, okay? So see, pretty easy there to use function notation, right? It's really very simple. It looks more complicated than it really is in practice. Sometimes students wonder about what's the significance of function notation. Why do we keep talking about function notation? so much. Instructors tend to really dwell on that a lot. And well, the reason is we're going to use it a lot, okay? And function notation was invented sometime in the 1700s, and that's really a very significant event in the history of mathematics. So it seems very kind of innocuous and not really very important, but function notation really turned out to be it's a really extremely useful idea, and it was really a great turning point in the history of mathematics when it came about in the around the middle of the 1700s. Okay, by the way, that's after the invention of calculus, because Newton developed calculus in the middle of 1600s. So function notation is quite a bit newer, about a century newer than calculus. All right, now let's look at some examples of using function notation. All right, so we're referring to that same formula. Let's see if we remember what that. So I'm using that same function as an example. So I think that was minus 0.22x plus 78, right? That was the formula for that function. So the first thing that you're asked here in this example is interpret the meaning of f of 20, okay? Interpret the meaning of f of 20. That's kind of a strange math instruction, right? Okay. But interpret meaning, you know, you don't often hear that in math courses, but that's important for function notation. So what do we mean by interpret the meaning of f of 20? Notice it doesn't say calculate f of 20. The instruction is not calculate f of 20. The instruction is just, what does that expression mean, f of 20? Okay. Anybody want to volunteer a suggestion for that? So what does f of 20 mean?
You're basically asking us to plug in 20 for x.
Wait, I can't hear you very well. Can you?
Sorry. Yeah, my laptop microphone is really, really bad, but
Oh, okay. So you may have to shout, but go ahead. I can hear you now.
So I think it's trying to tell us to plug in 20 for x, which means like 20 years later or something.
Yeah, that's very good. That's a very good start. Indeed, 20 means 20 years later than what year there? What was you remember what our initial year was? Is it Donna?
Yeah, that was me, but no, I actually don't remember the initial year.
It was 1990. Okay, so so indeed, this means 20 years after 1990. All right. So, but Donna, let me point out something to you here. Okay. So you're off to a really good start. Okay. If you wanted just to indicate, that we're dealing with 20 years after 1990. So if that's what you're trying to, write down in mathematical notation, all you would have to write is x equals 20. Okay. If you wrote x equals 20, that in math, that's enough to indicate, we are 20 years after 1990. Okay. So, but notice f of 20 is a little bit more complicated, right? Okay. So it is true that in this expression, x is 20. Right, okay, because 20 is inside the parentheses, so that's the input quantity, all right? So you are right that x equals 20 here, right? But that's only part of the whole expression where we have f of 20. So when we say, when we write down f of 20, it's something a little bit more than just x equals 20. All right. So let's see if we can figure out what more is meant here. Remember, look up here. Y, right, is f of x. So you can think of, when I write f of 20, you can think of that as being y. Okay. So what we're really referring to here is, in this expression, is not the X value, but what we're really referring to is the Y value. What was the Y value in this story, in this context? What was Y standing for?
Life expectancy.
Yeah, that's right. So F of 20 is really referring to life expectancy. Okay. So now we can start piecing it together. All right. So the meaning of this expression is Y, life expectancy. Now, Donna, now you can finish it off. This is life expectancy. What? When what?
It's 20 years later. Oh, when X equals 20. So
Yeah, when X equals 20, or so I could say when X equals 20. That's a little bit awkward to say it that way, though. Might be better to put life expectancy in, what would that be? 2010, because that's 20 years after 1990, right?
1990.
So here's the correct interpretation for that expression. So when you write F of 20, what you're trying to say is life expectancy in 2010. Okay. If you just wanted to say 2010, you could just write X equals 20. All right. Now, notice that when I interpreted the expression, we didn't calculate anything, right? So I didn't tell you what the life expectancy was in 2010. F of 20 just means life expectancy in 2010, right? So in this second problem, now we're going to actually calculate what F of 20 is, right? So that instruction, notice, is evaluate, or it could say compute, or it could say calculate. All right. Notice the difference. Interpret is asking for kind of an English explanation, right? Or I shouldn't say English, this could be any language, kind of a verbal explanation, correct? Okay. And then if we ask you to evaluate or compute or calculate F of 20, that means, that's where you're actually going to do some arithmetic, right? So, and that's what you're probably thinking is more mathematical, right? So you're probably more comfortable with this kind of instruction in a math class. So how do we evaluate F of 20? Well, we're just going to plug 20 into our formula. So that means we get minus 0.22 times 20 plus 78. What is that? I can do that. What is that? Minus 4.4, I think so. Minus 4.4 plus 78, which is something like 73.6, I think. I did that right.
You got it right.
Okay, so there's the instruction evaluate, right? Okay, that's where you actually do calculations. So of course we used our formula for this function to do this calculation. I want to point out you also could have used the graph. We had a graph of this function, right? So instead of using the formula, we could have come up here, and if I can find the graph, we could have looked here on the graph, right? And let's see, where's 20? 20 is, I think, right here on the graph. So we could have looked on the graph and try to figure out, what this matching Y value is. Okay, that's hard to read off of the graph, though. So it's easy to use. It's easier to use the formula. But you also could have tried to evaluate F of 20 by using the graph. Okay. All right. So a third part here, and then I'll let's look at this part C. So it says express in function notation. So here we have a sentence written out, right? It says life expectancy in 2015 was 72.5 years. Okay, so there's a fact written out in words. How can we write that in function notation? So if we want to compress that into mathematical notation, how would that look in mathematical notation? Okay. All right. Well, let's just take it one step at a time. Life expectancy in 2015. So how would you express that in function notation? Look up here as a guide for you. Remember F of 20, right? f of 20 meant life expectancy in 2010. So how can we write life expectancy in 2015?
F of 15?
F of how much there? 5?
15?
Not 15. Remember, we're counting years after 1990. So
Oh,
how
I'm
many
sorry,
years?
25.
25, right? So you would write f of 25, okay? So that means life expectancy in 2015, that's f of 25. Now, you want to say was 72.5, right? So how do you take this part and convert it into math? What does the word is? Equals. Yeah, I was going to say, what does the verb was or is look like in math? It's equals, right? So you would write equals 72.5. There you go. Okay. So they're just taking that sentence and rewriting it as a mathematical expression. Okay. All right. So that all looks kind of, fun, but not really all that important. But actually, function notation, as I mentioned, there turned out to be a really important advance in mathematics. It's really a great conceptual tool in mathematics. All right, before we get back to practicing a little bit with function notation, I've got some graphs for you here, and I just want you to see if you can answer for me which of these, remember, graphs are relations, right? So which of these relations that I've got represented as a graph, which of these is a function? So let's start with this first one. Y'all think that one, is that a function? That's a pretty simple, of course, there's the graph, right? This is just a set of axes. So I want you to concentrate on the graph there, right? Okay. So is that a function? So remember, what are you trying to figure out if it's a function? You have to know what each x matches how many y's?
Just one.
Just one, right? Okay. Is that true here? So do you have any x's that match two different y's? Well, you can just kind of experiment here. If you pick an x, right? So let's pick this x just for fun. And so on the graph, how many different matching y's are there? I only see one, right? Mm-hmm. See, if you go up to the graph and then come across, you're just going to have one matching y, right? Okay. And I think that's going to be true because this graph is a nice straight line, right? So I think that's going to be true no matter what x you pick. There's nothing special about this one. If you pick any other x, go up to the graph and find the matching y value, you're going to have only one, right? So so the answer to here is yes. This graph is that is the graph of a function. So answer there is yes. By the way, here's the way in mathematical notation of asking the same question that I just asked. I ask in words, is y a function of x? Here's how you can express that mathematically. Y equals f of x was a question, right? Is y a function of x? So there's the mathematical language for that English language question that I just asked. All right, let's look at some other graphs here. I got a few drawn. What about this one?
No.
No, yeah, definitely not, right? Not a function. So circles are not going to be functions. So they're perfectly nice graphs, perfectly nice relations, but they're not going to be functions, okay? So remember I told you, function graphs do not have loops in them, okay? That's one of the reasons why we're interested in functions. But if you want to think of it more technically, look, if you pick an x value, right, here, so pick a value on the x-axis, notice that and there are lots of instances like this, right? Notice that x value is going to match two different y values here, right? One on top and one on bottom. And so you cannot have a function, right? Because in a function, x can only match one y, all right? What about this one over here on the right?
Yes.
Yes, that does count as a function. Now that's got some curves in it. So don't think function graphs don't have curves in them. They're not always straight lines, Okay, but again, it's going to be the case that if you pick an X, so you just have to kind of visualize this. If you pick some X value here on the X axis and then try to figure out how many matching Y values it has, that matching Y value is right here somewhere. There's only going to be one. All right, so there's no way with this graph to pick a single X value that has multiple matching Y values. Okay. So yes, this is the graph of a function. What about this last one here, kind of in the middle there?
No, that's not a function.
So I've kind of taken this one and turned it on its side, I think, right? Yeah, I think that's kind of what I did there, right? I took this one and kind of rotated it 90 degrees, but no matter there how it came about, you're right. This is not a function. All right, so on a quiz, for instance, if I were to ask you, is this a function? No would be correct. But if I ask you, why is it not a function? Then you have to give me a little bit better explanation. And what you could say is, for example, oh, well, look at X equals 0. If you take X equals 0, how many matching Y values does that X value have? All right, so here's X equals 0. Well, it's going to have one up here, and it's going to have a Y value, matching Y value right there, and it's going to have a matching Y value right there as well, right? So that X value 0 has 3 matching Y values, and that's definitely not a function, right? So it's a nice relation, but it's not a function. So for the first part of calculus here, we're just going to throw this kind of out of consideration, right? We're not going to consider relations like this one, okay? They're going to make our calculus work a lot easier if we throw out this sort of case. So we'll only be concentrating on situations like this one, for example, or of course, very simple situations like this one. This is just a straight line, okay? So you can't get a much simpler graph than a straight line, right? Okay. All right. So before I come back and I'll let you do a little bit of a practice here. But before we do that, we've already gone a while here. So let's take a break till about 12:30. All right. So I have 12:24. So let's stop till about 12:30, and then we'll come back and look at this example. I'll leave it up here so you can see part of it. I don't think I can get the whole thing on the screen at once, but you can see the first. By the way, when y'all are looking at this, can you see the graph? Is the graph obscured, or can you see the whole graph?
No, we can see the whole graph.
Okay, yeah. So yeah, that's because I have a hard time knowing what y'all are seeing and what I am seeing. So okay. Great. So that's fine. All right. So we'll come back at 12:30, and then I'll let y'all. You can work on these in the meantime, but I'll let y'all work on these, and then we'll share our answers. Okay. All right. Okay, guys, I'm back. So let's resume here, and so let's look at this. Fast example, just to give you all a little bit of practice here with the easy idea of function notation. So it says the following graph. Y'all can see it here on the right. That shows the approximate population of the United States T elapsed years after 1900. Okay, so so the input variable in this case is T, all right, not X, and that represents elapsed time. That's why we use the variable T after the year 1900. So this is going to be through the 20th century, right? And then does it go into the 21st century here? I can't see the graph very well myself. So yeah, it goes a little bit here. Well, actually up to current time, up to current, right? Okay. All right. So this may be a little bit of a, I'm not sure. I think it's a little bit of an overestimate. All right. So the output variable is y, and that represents population in millions, right? So first question there, it just says, give a description of the units of measure for input and output. So I just did that. The input quantity is elapsed years, right, from 1900, right? And so year 0 would represent 1900, year 100 would be year 2000, right? Okay. And the output here is y, that is population measured in millions, obviously, right? There's a lot more than 100 or 200 or 300 people in the United States, right? So the output here is measured in millions. Very first question there is y equal f of t, right? So that's how you read that expression off the page, right? Y equals f of t. But if you convert that into English, right, what are we really asking when we write y equals f of t? So what's the really correct way of asking this question in words? Anybody just want to tell me that? So what am I really asking there when I write y equals f of t with a question mark?
Is y a function of t?
Perfect, right? Yeah, you're just asking, is y a function of t? In other words, is the in other words, there, Lewis, is the population a function of elapsed time? Okay, Lewis, what's the answer to that question? It's just a yes or no question. So, which one is it?
Yes.
Yes, yeah, it is, right? Okay. And that's just because of the shape of that's just because of the nature of the graph, right? Okay. If you you don't have a straight line here, but you have a pretty simple curve, right? And so anytime you pick a t value, right? Okay. Anytime you pick an elapsed year, if you use a curve to estimate the population in that year, right, you're going to get only one population estimate, right? It'd be silly to get two population estimates, right, in the same year. So definitely want a function in this situation. For instance, if I pick elapsed year 60, that would be 1960. Okay, then we can, of course, use the graph, right, to estimate what the population was in 1960. It looks like, can't read these tick marks very well. I'm not sure what that is. It's a little bit more than 100. I'm not sure how this is. Oh, wait, 1, 2, 3, 4. Oh, these are in increments of 20, right? So it looks like in that year, 1960, we could estimate that the population was 160 million there in the population was 160 million there in the United States. Okay. All right. So, all right. So here are the parts that I'm going to leave to you really quickly here. The next couple of parts of this question. So let's just take a couple of minutes on this. Okay. So interpret f of 40, interpret f of 40, and then evaluate or calculate f of 40, right? So those are slightly different instructions. I'm sorry, evaluate f of 120, okay? And then see if you can answer this question. When did the population first reach 200 million? So I know you're looking at this graph on your screen, so your estimates are probably going to be a little bit rough, right? Okay, but just do your best to answer those three things, right? That won't take very long at all. Just interpret, right? Remember what we mean by interpret, evaluate, and then see if you can answer this question, which is kind of opposite here. What year, right, did the population of the U.S. first reach 200 million? Okay. So take a couple of minutes for that, and then be sure you're giving it your good shot, right? Because I'm going to ask some people to share their answers, or we'll have the class help you with your answers, okay? If you're stumped a little bit. Okay, so let's try this. Because these are usually pretty easy, especially when you're dealing with a graph. Okay, all right. So I had some names that I already picked out before class, but some people have already jumped in. So you guys are lucky if you've already answered a question for me. You've already fulfilled your duty here. Let's try Daniel. Is Daniel there? Daniel Adego? Adigo?
Yes, I'm here.
All right, so Daniel, can you help us with the first question there? C just says interpret f of 40. So how would we interpret f of 40? That interpret means what does something mean? So what does f of 40 mean to us?
Like f of 40 means like f is like y equal f of x.
Mhm.
F of 40, what's the y value when is f is 40?
Okay, so yeah, it means you got that right. It means it is the y value. Let me write down what you said, kind of. But y value when x, it's actually t here, but same thing. Y value when t is 40, right? Okay, yeah.
Yeah.
So that's correct, Daniel. But what we want to do is now we want to take that and extend that interpretation a little bit more. So all you have to do to make this a really nice interpretation is what is y? So what does y mean in this problem? What is y representing here?
80, I think, on this.
No, just in general, what does y mean? So what do all these y values, if you look at all these values plotted on the y-axis, what are all those
the
numbers mean?
population?
What, say that again?
The population?
Yeah, that's population. So so instead of saying y value, let's say population, okay? Because that's what y is. So population when t is 40. So what does t equal 40 mean? There's t equals 40, but in the context of the problem, what does that mean? When t is 40?
T is the time or the year?
Yeah, it's the year, but it's not year 40. It's year. What's the proper calendar year when t is 40? Remember,
1940?
what? Say that again.
1940, I believe.
Perfect. Right. So altogether, Daniel, if you just put those things together, you could write down population in 1940. See what I'm getting at there?
Yeah.
So yeah, so see, that's how you would if you were explaining this to your grandmother, right? Okay, what f of 40 means, you would say population in 1940, right? Okay, then she could understand that. All right. All right. So that's excellent, Daniel. That's exactly the way we work through this. That's exactly the way we work through this process. Okay. All right. So now, on the other hand, evaluate is a little, again, as I mentioned, that's a little bit more standard type of problem. That's a little bit more mathematical. Okay. So Malcolm, you came in first. So are you still here? I'll pick on you since you got here early. Can you tell me what, when I say evaluate f of 120, what is that? Are you still there, Malcolm? I think Malcolm was chatting with me earlier, so you can just chat it to me, Malcolm, if you want to. Okay, so Malcolm says he's thinking about it, right? So Malcolm, let's help Malcolm think here. So so evaluate, Malcolm. That sort of means the same thing as compute or calculate. So when you see evaluate, you can think, oh, I've got to calculate f of 120. So that means you actually have to give a value for. You actually have to give a value for 120, right? So it's not a matter of writing it out in words. It's a matter of actually giving a value for f of 120. So how do you using the graph? How do you figure out what f of 120 is using the graph? Malcolm, can you do that? Can you see that on the screen? Okay, so yeah, so you can see it there. So just eyeballing it as best you can, what do you think there is f of 120? While Malcolm is thinking about that, does someone from the class have, you can suggest something to Malcolm here while he's doing this. Anybody want to suggest to Malcolm how he can calculate f of 120?
Is it 0?
Is it
Oh,
0?
not 0. Sorry. Is it like it looks to be about 20 or 10 or 120? Sorry.
So is that who was talking to him? Is that Saad?
No, this is Lance. Is it 100? It looks about to be 100.
F of 120 looks to be about
Oh
100.
no, I'm sorry. I was looking at the y-axis. Is it 20?
Okay, all right. So let's talk about how you're getting those numbers. All right. So what did you do with the graph to find the number that you found there?
I'm looking at the y-axis right now,
Uh-huh.
and I'm
Oh,
supposed to
I
be looking
see.
at
So you're finding
the
a
y-axis,
120 on the y-axis
yeah.
and then going backwards?
Yeah, I should be going on the t-axis, right?
Right. Yeah, because this
Oh
is
yeah,
the
my
t.
bad.
Yeah, this is the t value. Yeah.
Yeah. Oh,
Okay.
yeah. Oh, yeah, it's 400 then.
There you go. Right. Okay. Yeah. So t is 120 here. So find 120 on the t-axis, and then try to draw your a vertical line up, right, till you get where you're going to get to this point, because that's the end of the graph. And then you come back across, right, horizontally, and come back across there horizontally, and it looks to me like it's coming out right there, that is not quite. I know it's hard to read from your angle. It's really closer maybe to 360 than 400. Actually, that's a little bit too high, because the actual population currently of the United States is a little over 330 million. So when this graph was made, this graph overestimated there a little bit. Okay. All right. So, but the process described there is, you're right. Okay. So that's how you evaluate. So you come up with a number, right? You come up with a value here when you're told to evaluate. What about E there then? Thank you, Malcolm. So what about E there? When did the population, at least according to this graph, when did when the population first reach 200 million? So let's see who else is on my, everyone's gone through my list here. Let me ask, Calvin's here, right? Calvin? So can you answer that? You can chat it if you want to.
Can you hear me?
Yeah, I can hear you.
When is the population first
Yeah, so
reached it around
what now?
70 years afterwards, 1970?
Around 1970? Okay, so how did you arrive at that? How did you arrive at that number?
So since the population is Y, I just looked at 200 million on the Y-axis.
Perfect. And then you just read the graph backwards, right? So you came across here and then came down, and yeah, you're pretty accurate there. Yeah, that is right at 70. Okay, so so according to this, it was right at right there at 1970. Wonder when the population really did first hit 200 million. Seems like I recall that from when I was a kid, and it was a little bit before 1970. So, well, okay, we could question the accuracy of this graph, but anyway, that's how you would. You're right. That's exactly how you would read that. Okay. Okay. So, all right. Very good. Y'all did really good there. Okay, let's trying to scroll here down. So all right, now these questions are a lot less applied. Okay, so here we're given some function rules in the form of formulas. Okay, so here we have first a function called f, and there's the formula for the function f. So notice this is not a linear function because it has the square on the input variable x. And then here we have another function, also not a linear function, called g. And we're just asked to evaluate a bunch of expressions. So no interpretation here, just calculations. All right. So if you just have a simple number as an input, most of y'all can do this really easily. All right. So if we wanted to evaluate f of -2, see, that means let x be -2, right? Then you can do that. All of y'all can do that arithmetic pretty easily, right? So all you're going to do is take the -2, of course, and substitute it into the expression for x, and then you just have a little bit of arithmetic to carry out. The only thing I wanted to point out in this example is be careful. Remember, and I mentioned this a couple of times already, when you're plugging negative numbers into expressions for variables, I think it's always safer to put the negative number in parentheses in the expression. So you might feel like you don't need to do that, but that will improve your accuracy some. Well, when I say improve your accuracy, that will help you avoid making mistakes. All right. So when I took the -2 and plugged it into this formula for f, that's why I put the -2 in parentheses. And now you can just carry out the arithmetic. So that's so easy. -2 squared, of course, is going to be +4, right? 3 times -2 is -6. And then, of course, we have that constant -2 at the end. So we end up here just getting 8 - 6 - 2, which looks like 0. Okay. Oh, so what does that tell me about the number -2? That tells me this is going to be an x-intercept, because when x is -2, notice that f of -2 or y is going to be 0, right? Remember, you find x-intercepts by setting y to 0. So it looks like one of our x-intercepts for this expression is -2. So in other words, if we were to make a graph of this function, it would cross the x-axis at -2. All right. Now, what's going to be trickier for you, and is often the source of error in calculus, is not evaluating functions at numerical inputs, but it's evaluating functions at symbolic inputs, and we have to do that frequently in calculus. All right. So this is where students sometimes get a little bit messed up in their algebra. All right. So suppose, for instance, we want to evaluate f of a. Okay. This expression and this expression mean the same thing. We're going to substitute a for x in the formula for f. Okay. So don't think this means something unusual. It means exactly what f of -2 meant. So you would have 2 times a squared plus 3 times a minus 2. Okay. So again, don't let this a symbolic input, the fact that we're using a variable here as our input value, don't let that throw you off. Okay. You evaluate the expression exactly the same. Just substitute the a for x in the formula for f. and you just end up with this as your answer. This is this expression is your final answer. All right, so let's look at g of x plus h, okay? So here's the formula for g, right? There's the formula for g, and I'm going to use as input x plus h. So again, this looks, sometimes to students, this looks a little bit strange, okay? That we're using this expression, x plus h, as input to this function. But the process is exactly the same. So even if this looks odd to you, you can still carry out this evaluation. You're going to take the x plus h and you're going to substitute it for x in this formula. So I take all of this, and I substitute it for x in this formula, right? So I get what? X plus h squared plus 3 times x plus h, and then plus 2. Okay. Exactly the same process as evaluating f of minus 2 or evaluating f of a. Take that whole input inside the parentheses and substitute it for your input variable in your function expression. Now you have to do a little bit of algebra though, okay, because we want to simplify this answer. So I have to take x plus h and square it. So when you square a quantity, remember, that means you multiply it times itself, right? So you're going to get x plus h times x plus h. Here's what I do not want you to write down. X plus h squared is not equal to x squared plus h squared. Everyone got me there? Okay. X plus h squared is not the same as x squared plus h squared. All right. This mistake, by the way, is called freshman's dream. And I do not want you to make that freshman's dream mistake, okay? So be careful when you're squaring expressions. Remember, you're multiplying them by themselves. The second part here is easy. 3 times x plus h, that just means 3 times x plus 3 times h. And then we have the plus 2 here, right? All right, so let's keep simplifying. Let me leave myself a little room here. So x plus h times x plus h. Well, how do we multiply these two parentheses together? You take x times x is x squared. You take x times h. I'm going to write that as h times x. I always like to write my variables in alphabetical order. So instead of writing x times h, I'm going to write h times x. Here's h times x again. So you get 2 of those. And then h times h is h squared, right? How do you multiply these parentheses? X times x times h times x, h times h, right? Plus 3x plus 3h plus 2. And now continue simplifying. That means I'm done with the multiplication, but now I can add like terms together. The only like terms I see that I can add together are these two, however, right? Those are both hx terms. So when you take hx plus hx, you get 2hx. So you have x squared plus 2hx plus h squared plus 3x plus 3h plus 2. There is your big, ugly final result, okay? That is fully simplified by hand. You cannot carry out any more of the arithmetic in this expression by hand without having a value for x and without having a specific value for x and without having a specific value for h. So you would have to leave your result just like this. That's all you're being asked for. Okay, so get my pen working again here. So we have to do a lot of these manipulations with a lot of these evaluations with function notation. And students often, this is often a source of mistakes for calculus students because you have to do this a lot and it's easy to make errors. So you don't want to make those simple algebra errors. So what if I'm trying to evaluate f of a minus 2? What is that? What is this expression? Well, that's pretty easy because we already calculated f of a moment ago, right? What was f of a? That was 2a squared plus 3a minus 2. So all you have to do is just, wherever you see f of a, right, since we already calculated that, just take that and substitute it in here. So you have 2a squared plus 3a minus 2. And then don't forget, you've also got this minus 2 that was part of the original expression. So what's the final result? It's 2a squared plus 3a minus 4. So there's my final answer there. Now notice these two expressions are slightly different. Here you have f of a and then minus 2, and here you still have f of a minus 2, but the minus 2 is in parentheses, right? It's in the parentheses. So what's the difference between D and E? Well, so I want you to calculate for me, this one, f of a minus 2. And I've actually got a couple of them that I want you to calculate for me. So f of a minus 2, and then also this one, g of 2x. Let's save that for a minute though, and let's try this one first. Let me show you let me remind you of the formula for f, because that's up a little bit higher. So remember, f of x, its formula was 2x squared plus 3x minus 2, right? Okay, so there's the original formula for f. So use that now to compute for me f of a minus 2. All right, so use that formula to calculate this for me. Can y'all do that? Let's take about just a couple of minutes there. See if you can grind through that arithmetic to calculate f of a minus 2. If you can do that one, you should feel pretty good about the algebra you're going to have to do for the rest of the class. See, that's not too bad, right? So if you got through that, then that will help you with a lot of the calculations we're getting ready to do. So work on that. Well, just don't take too long. So try to work quickly. If you don't get completely finished with it, that's fine. We'll finish it up as we're discussing it. So is everyone working on that one? I'm gonna pick on somebody here in a minute. So just keep working on it. Okay, did y'all sort of get somewhere in those calculations, if not completely finished? Yes, no, maybe?
Almost.
Almost. Okay. All right. So I'm going to pick someone, and then we'll finish it if we have to. All right. So Alba, you answered a question for me a moment ago, right? So let me, Alba, are you there? So see if you can help me with filling this in. Can you turn your mic on, or you can also just tell me on chat sort of what to do, and I can do it for you. Alba, are you there? Oh, there you are.
Yes.
All right. So.
Do I tell you the answer or like just
well, just try to tell me the steps, and then we'll get to the answer really fast. So kind of just, what did you do first?
The first thing is I replaced x with a minus 2.
Right, perfect. So you got, I hope, something that looks like this. Is that right?
Yes.
Yeah, and then when you started simplifying that, you can maybe skip down to the next to the last step or something. So when you started simplifying this, what kind of where'd you get at before the answer, before you completely finished?
Close to the end, I was at 2a squared minus 8a
Minus 8a
plus 8
plus 8. I
plus
think that's
3a.
Oh, could keep going.
Minus 6 and minus 2.
Perfect. Yeah. So once Alva squared the a minus 2, so remember that was a minus 2 times a minus 2, right? And so she multiplied a minus 2 times a minus 2, and then she multiplied in the 2. She got this 2a squared minus 8a plus 8. Okay. And I think that's right, Alva, I think. Okay. So, oh, by the way, some of you, when after you got to this point, you might have been tempted to multiply the 2 in first, like this. Don't do that. Okay. All right. You must square the a minus 2 first, and then multiply in the 2 in. I think that's what Alva did. Okay. So do not multiply the 2 in first, and that would give you 2a minus 4, and then square it. That's going to give you the wrong answer. First square the a minus 2 and then multiply in the 2. That's the order of operations. Remember, in the order of operations, exponents take precedence over multiplication. So, okay. So this is right, Alba. And then what was your final answer there? Now it's
Final
easy, right? Go ahead.
2a squared minus 5a. That's it.
2a squared minus 5a, and then that's it? Yeah, that's it, because this is 8 and this is negative 8. So those cancel each other. So that's it. Yeah, we just end up with 2a squared minus 5a. Does someone have a question there? Anyone have a question about that? Someone was talking, so I don't know if they had a question or not. All right, now let me show you also two other quickly here, slightly different expressions. Okay, look at these two. Here we have 2 times g of x, and then so that's how you would read that off of the page. And then we have g of 2 times x. See, so this is 2 times g of x, and this is g of 2x. All right, so those look similar to each other. It's just the position of the 2, but they're actually quite a bit different, right? And again, it has to do with the order of operations. I forgot the formula for g. What was that? X squared plus 3x plus 2, right? X squared plus 3x plus 2. Let me write that down. So g of x is x squared plus 3x plus 2. So when you're calculating 2 times g of x, all you would do is fill in for the g of x what its formula is. So you would take x squared plus 3x plus 2 and fill that in for g of x. So you would have 2 times x squared plus 3x plus 2, right? See, this is g of x, and you're multiplying 2 times g of x. So you just get 2 times all of this. So that's real easy. That's just 2x squared plus 6x plus 4. The reason this one is different is you're going to take the 2x and substitute it for x in the expression for g. So this would give you 2x squared plus 3 times 2x plus 2. And notice that's going to come out to be quite a bit different. But when you simplify this expression, it's going to be quite a bit different from this one. All right. So I'm not going to fully simplify this one. You could go ahead and finish this by squaring the 2x and then taking the 3 times the 2x and then adding on the 2. But notice that will not come out the same as this. So 2 times g of x and g of 2x, those are different from one another. Let's look at these last two here quickly, and then we have just enough time to finish these, okay? So this one is very straightforward. You just have to make sure that you read the expression properly. So this says we're going to take f of x and divide it by g of x, okay? So take f of x and divide it by g of x. Well, that's really simple. If you can remember the formulas for these two functions, right? You're just going to take the quotient of these two formulas. So the formula for g, that's easy. That's x squared plus 3x plus 2. So that's what's going to go on the denominator here. And I forgot the formula for f, so let's remind ourselves of that. Oh, that was 2x squared plus 3x minus 2. So in the top here, you would have 2x squared plus 3x minus 2. There it is. That's just f of x, because this is what f of x is, right? And then divided by g of x, this is what g of x is. So you'll end up with this big quotient, this big fraction with these two expressions in them. Now, this one we want to look at really closely, all right, just to make sure that we evaluate this expression properly. So the way you read this off of the page is, think about your function notation. You read this f of g of 2. So please don't be saying fg2 or f times g times 2. Make sure you read it like function notation, f of g of 2. All right, now how do we actually evaluate, though, this expression? All right, this is where order of operations is really important to help you evaluate this expression. Remember, in order of operations, you always work from the inside of parentheses out, okay? Inside out. So you are going to, well, first you would work inside this innermost set of parentheses, and you would try to simplify 2. But look, 2 is just a number, so you can't simplify 2. 2 is 2, right? So that's already simplified. Next, again, work out a little bit. So next, you're going to calculate g of 2. G of 2. Well, what is g of 2? Well, there's the formula for g. So we find g of 2 just by taking the 2 and plugging it into this formula, right? So we would get 2 squared plus 3 times 2 plus 2. Do that arithmetic and then apply the function f, right? See, you're working innermost parentheses out. So let's see, what's 2 squared plus 3 times 2 plus 2? I think that's 12. If I did that right, 2 squared is 4 plus 6 is 10 plus 2 is 12. So now we have f of 12. Now we calculate f of 12 just by plugging 12 into our formula for f, right? So we have 2 times 12 squared plus 3 times 12 minus 2. And then we just have to do that arithmetic, and that's it, okay? So just simplify this arithmetic. Let me see if I can do that quickly in my head. This is, you can use a calculator if you need to. 2 times 12 squared is going to be 288 plus 36 minus 2. So what's 288 plus 36 minus 2? What is that? Is that 322? Am I doing that right? No. Am I? I think so. Yeah. Okay. So y'all can check me on that. So I think finally that comes out to be 322. Okay, well, we're just about out of time. There's only one other sort of general topic about functions that I want to mention, just general topic about functions that I want to mention, and then we're ready to actually start talking about important features of functions, and that's really where we're headed toward, okay? Because calculus is going to be the study of important features of functions. You don't have, calculus doesn't have to restrict itself to functions, but we're going to restrict ourselves, again, as I mentioned here repeatedly, to functions here at the beginning. And we're going to talk about 3 important features of functions beyond these basic features of functions that I've already talked about here. Okay, so this last important idea I want to introduce with functions, and I know you've heard these terms before, so I just want to remind them because we use them all the time. When you have a function, actually this applies to relation too, but most of the time we apply these terms to functions. When you have a function, you have 2 sets associated with the function. One set is called the domain. That's the set of all input numbers for the function that are going to give you meaningful output values. All right. So think of domain as being the set. Domain is a set. So domain is a set of input numbers. And then opposite to that is the range. That's the set of output values for a function. Okay. And again, since we're working with functions so much in the course, these terms are going to come up frequently. Domain means what are the input numbers for a function, and range just means what are the output values for the function. Okay. We want to just next time just briefly explore these definitions since we're going to be using them so much. And I know you've heard them before. So just to remind ourselves of what these things are, right? And then finally we'll arrive at, well, what are the features of functions that calculus is really specifically focused on? All right. I mean, these are general ideas for functions, but what are the features of functions that calculus concerns itself with mostly? All right. Well, we've run ourselves out of time today. We're exactly at 1:15. Do y'all have any quick questions here before we go? So remember, there's a homework due tomorrow, right? But it's real short. So if you haven't already done that one, you can finish that one really quickly. I think it's only 8 questions, and I think they're pretty easy questions.
The homework that was due Saturday, it was just one, right? It was the review algebra one.
Yeah, it was the algebra review, right? Yeah, that was
okay.
due on Saturday. Yeah, okay. So there's one due. It was one due today, but I moved it back a day just to give you a little bit extra time. Most people are done with it, and the people who have done it have been making 100. So I know it's not hard. Okay, so don't be so get started on it. You'll finish it quickly, and then you'll be glad you're done with it if you haven't already done it. Okay. All right. So any other quick things there? Great. All right. So I will see you on Thursday, right? Okay. And we're going to introduce some of our calculus ideas, and but we're going to do them really in a really gentle way. So you'll find them really easy to understand initially, and then of course it gets a little bit harder. All right. So I'll see you guys on Thursday. Let me stop the recording now.